Hi, welcome to Calculus 2. We are going to continue our lecture on integration by parts. In the previous lecture we talked about the concept. Today we are going to take a look at some basic examples. Let's see what is the story here. Okay, so last time we explained what does it mean to write u dv is equal to uv minus integral of v du. We want to use that concept to solve these four problems. So I have four problems listed here and we are going to solve them, and we emphasize that all steps are to be shown. I'm sure everybody knows there are various software and websites that give answer to these kind of things, but what we are trying to show is that we understand how to apply this procedure for calculating it. So that's what you are going to be expected to show in your written or in your oral presentations. Now during this I'll try to encourage everybody to do as much of this as possible. So every now and then I'll ask you to pause the video and try to finish the problem yourself, or at least make some advance and think about what to do next. To signal this to you, I'll just put that picture again so that that will be a signal that you are supposed to participate in the lecture and try to make some advance by yourself. Okay, so let's go ahead and get started. So last time we talked about this. Now let's go to apply it in one basic example. I have integral of x dx. So x exponential of 3x dx. We want to match the terms that we have here to the terms that we have in this general approach. And of course it's not immediately clear who's going to play the role of u and who's going to play the role of dv. We are going to practice a few of these things, and later on we are going to give some general guidance for doing this. But in principle you have to do trial and error to see what works and what doesn't. In some basic simple examples we can give you some blueprints to follow, but in general there isn't such a simple blueprint. Okay, in this case keep in mind that after you exchanging v and u, your hope is that the right hand side is simpler integral than the left hand side. So here if I take u to be x, when I go to the other side, du is just dx, and that term is going to disappear. So that's my motivation for taking this and split it in the following style, that I'll say, okay, let u to be x, and then dv is whatever is left. So e3x dx, that's going to be my dv. Let me write it better here. Okay, on the other side I need my du. How do I calculate du? Du simply means the derivative of u times dx. Well, derivative of x is just 1 times dx. Now here I need the v in these two locations. What is v? So differential of v is given to be exponential of 3x dx. If you wish, you can write this statement like this, that dv dx is exponential of 3x. So what is going to be v? V is going to be antiderivative of this. So from calculus 1 you're expected to know what the antiderivatives would be, and you're expected to know this one rather quickly. So exponential of 3x, if you integrate it and find the antiderivative of it, it'll be exponential of 3x divided by 3. We could have added a constant here, but that's going to just crowd the picture and not going to help anything. So when we calculate the v, we dispense with that additional constant just to make our problem a little bit easier to follow. Next, well, I have to calculate u times v, but this is the u, this is my v, so it's going to be x exponential of 3x over 3 minus v, here's a v, exponential of 3x over 3, then du, which is just simply dx. Let's make a separation between this and the calculation that we are doing here. So what do we have achieved? We had this expression here whose antiderivative wasn't in our basic tables of integrals, but after integration by part I have this one whose antiderivative is in the table. Actually we just did that. So that is the point of integration by parts, that when you go through this process, the right hand side will be simpler than the left hand side, and therefore you're closer to the exit. So here I write again exponential of 3x over 3. Antiderivative of exponential of 3x is going to give another factor of 3 in the denominator, so it becomes exponential of 3x over 9. There was a 3 and another 3 is coming, and in the last stage we have to include that constant. Here we didn't need to bother with that, but here if we don't include this constant we are off. So here's our final answer. So we can write it like this: x exponential of 3x sorry, is x okay. Now it's a good practice for you, after you have seen this thing, to go through all of these steps by yourself again, and let me ask you to do the following without looking at this screen as much as possible. Try to do this. Okay, so reproduce all the steps and come up with the final answer. Okay, not by guessing and not by using some software or a calculator or a website or any of these things. You just sit through the calculation from beginning to end. Let's go ahead and do another example. So next one up is something with a logarithm in it. Let's see, what do we do? So integral of x squared logarithm of x dx. Well, again the question is up. Should I take u to be, say, x squared and dv to be this? Or should I take u to be, say, logarithm of x and dv will be whatever is left? So we have some options. Let's see what options we have. We could have taken, for example, u to be x squared and whatever is left is dv. You see right off the bat that we are going to have an issue. du, I have easy way of calculating what du is, but v, well, I actually have a challenge in front of me as to what is the antiderivative of logarithm of x. So it could be that that's a good way to go, but that doesn't look that way. So we put that on ice for now. So okay, this doesn't look like promising. So we go after some other options. There are many options here, but let's see. If we take u to be logarithm of x and dv is taken to be x squared dx, well, when I calculate du and when I calculate v, I come across expressions that are all easy for me to handle. That is, here I take du, the derivative of logarithm, is of course just 1 over x. And v here, antiderivative of x squared, that's going to be x cubed over 3. Okay, again, no need to bother with the constant here. So when we talk about the integral u dv is supposed to be equal to u times v minus v du. So u times v is going to be x cubed 3 logarithm of x minus v du, that's minus this expression which is x cubed over 3, that expression which is 1 over x dx. So we separate our preparatory step here from our calculation. So I have x cubed over 3 logarithm of x, and this becomes of course just x squared over 3 dx, and out comes x cubed over 3 logarithm of x minus x cubed over 9, and then of course I have plus a constant. Okay, feel free at any stage of this to stop the video and just try to complete the problem yourself. So it would have been a very nice gesture on your part to stop the problem right here and do all of this thing yourself. But here let me ask you to do the following. Suppose I tell you what is x, say, to power of 5 logarithm of x dx. What is that? Okay, so here is our official signal to you. You try to do the problem yourself and stare at that picture, get some inspiration maybe, or just stare at the picture. So let's go to another example. Sometimes the problems look a bit odd in that we don't even see two pieces in it. Say logarithm of x, integral of logarithm of x. That's the problem that stopped us in this track over here. What would that be? Well, we tried the same approach that we took here. Let's see. If I take u to be logarithm of x, then who's left for my dv? Sometimes the problem is so simple we get a bit confused. Well, dv is what is left is just 1, if you wish, 1 dx, just dx. So we become a little bit faster. du, let me see if I can encourage you to finish the problem. Okay, don't wait for me to do it. Try to finish the problem yourself. So du, of course, is derivative 1 over x dx, and who is dv? Excuse me, who's v? Well, v is just x. So u times v is x logarithm of x minus v du. That's just this x times 1 over x dx. Well, that's just 1. Integral of 1 is just x, and then we throw in a constant. Okay, so this is an important formula to know and to know how to derive it. Let's for the last problem for today, let's see. Suppose I want to do arc cosine of x dx. What's the antiderivative of arc cosine? So you end at calculus 1 with the table of derivatives and antiderivatives. You want to rewrite that table many times by hand, go from left to right, from right to left, so that all those formulas come back to your mind. And now we are going to make use of many of those things in our exercises. So here I want to calculate this antiderivative. What do I do? So again, let me see if I can just delegate it to you. It is a little bit more crowded than before, but if you get to do this thing, you have made a significant step forward, and then we like to talk to you, meaning we want to recruit you for mathematics. So let's see. So again, try to do it yourself. Several things. Like the previous problem, we probably want to try that u to be like this, just like u was logarithm of x over there. So I take u to be arc cosine of x, and whose dv, there isn't anything left now. dv is 1 times dx, it's just dx. So no surprise that v turns out to be just x itself. Now the question, what is du? What's the derivative of arc cosine? Again, it's a good idea for you to actually go try to rediscover where that formula itself came from. So to have calculus imprinted on your mind and be able to go far with it, you need to go back and rederive all those formulas from scratch to help you get a footing in it. Just relying on tables and such, it's not going to do it really. At some point things are going to fall apart. So let's just go do a mini review of calculus 1 as to what was the derivative of this thing. So let me just take a minute in parentheses. If you were back in calculus 1 and this was the problem, and then you wanted to find out what is the derivative of this thing, you well, you have the table, but where does the table come from? Let's see. This was in the section on inverse functions. So what I do is that I take a derivative from both sides, so it becomes cosine of y is equal to x. Now I take a derivative of this by chain rule. The derivative of this becomes what? Y prime. Derivative of this is sine of y with minus, and derivative of x is just 1. So y prime becomes minus 1 over sine of y. Well, if cosine of y is equal to x, what is sine of y? Well, since sine squared plus cosine squared becomes 1, therefore sine of y becomes 1 minus x squared. Now, why is it plus as opposed to minus? Because when you write y is equal to arc cosine of x, you are saying y is an angle in the first or second quadrant, and those angles have a positive sign, so that's why positive comes in here. So I have minus 1 over radical 1 minus x squared. That's what the derivative of u is going to be, and I just went through the derivation of what that is. Let me just do this thing again. Arc cosine of let's see, if it was arc cosine of x and I want to differentiate it, what would that be? It would have been minus 1 over square root of 1 minus x squared. Just for the completeness sake, if I had arc cosine of u, or let me use another letter, say w, derivative, I will have minus w prime by chain rule over 1 minus w squared. So that is the the derivative of this function. Now I realize that I wrote 3x here and then I wrote x here, so let me go make a correction so that we all have everything looking like each other. So let's see, this was 3x. Let me use that, it's a little bit more interesting. So the derivative of this we learned by this final rule here is that I have to take a derivative of this expression, which is 3, make that negative, over 1 over square root of 1 minus that expression, whatever it is, 3x squared. Okay, next. So this is my u, my v turned out to be just x, so u times v is going to be x arc cosine of 3x, and then minus v du. So this is my v, this is du. When I multiply it becomes minus 3x over 1 minus, this is 3x squared, then dx. Okay, we took that integral, we ended up with this integral, and then you might say, well, why is this any better than that? In fact, in some cases you go through this integration by parts, and what is on the right hand side is either as complicated as what you had, or perhaps even worse, maybe more complicated. But this one, I want to remind you, you actually have seen this in calculus. This is a standard problem there, and you can find this. So that integral turns out to be actually simpler than that. So let me ask you, put this challenge in front of you. How would you calculate this integral in methods that you learned back in calculus 1? How do you do that? So what you do is put the pause here, try to be like Jimmy Neutron or somebody, make that brain start to work, and you have to put yourself under a little bit of a pressure to get this thing done. Go perhaps review some sections and then come back. So make an effort not to be just a listener but a participant. So let's separate this thing that we have here. I have x arc cosine of 3x. Perhaps to clean up a little bit, I take this minus 3 out, so it becomes, let's put this thing in parentheses, plus 3 integral of x over, let's clean up the denominator also, minus 9x squared dx. What do we do now? Well, from calculus 1 you remember the idea of a u sub or substitution. Since we have been using the u's and everything else around here, let me use some other lettering here. So let's perhaps call it, what's a good letter? Say T. Say T, I take it to be the radicand. Why is that a good choice? Because I see the derivative of T here. So I go ahead and calculate derivative of T. It's going to be minus 18x dx. So over there I have the integral here. Let me just focus on this part. Integral of x over 1 minus 9x squared dx. So x dx, here's my x dx, it's just dt over 18 or minus 18. So this is dt over minus 18. And this is t inside the radical. So let's clean this up. I put the minus 18 out, and 1 over radical t, I can write it as t to power of minus 1/2, then dt. This is looking like those gift items in the shape of Russian dolls. You open one, there's another one in it. You open that one, there's another one in it, and then you have to open that one. Hopefully that's the last one, and we don't keep going on like this. So minus 1 over 18, and what's the antiderivative of that? So that's the most basic of formulas back in Cal 1. You add 1 to this thing, so it becomes t to power of 1/2, and then divide by the new exponent, which is 1/2, and when you clean this up, it's minus 1/9 of t to power of 1/2. You go back and write it as 1/9 of what was t? T was that to power of 1/2 means what? To power of 1/2 means radical. And then you put your constant also. So at the end, here's our final answer. X arc cosine of 3x plus 3 times this quantity, which was minus 1/9 of radical 1 minus 9x squared. And then you put a constant for the entire thing. You can write that any which way you want. And of course, you can simplify this to minus 1/3. So our last problem was a bit more twisted than all the others. Let me leave you one problem. What is arc sine of, say, 7x? What's the integral of this thing? Okay, so you practice that, and then there's a bunch of homework for you to do. And again, please do not use the software. Do not rely on copying from somewhere else or outsourcing it or this or that. You're supposed to go through the steps, and you're all capable of doing this. So we want to learn this. The concept of integration by parts is very important, and these are some basic examples. We want to make sure that we are up to speed with respect to doing that. Okay, until next lecture, good luck and God bless.